Hello everyone. This lecture is exclusively recorded for second year BSc student of BK Birla College, Kalyan. This is mathematics class. In this lecture, we will state and prove Leibnitz rule for derivative of integrals and problem based on Leibnitz rule, and we will also define the Riemann sum definition and problem based on it. So I have already written the Leibniz rule on the board, you can see. So it says that if you have a continuous function defined on closed interval a comma b, and g is a function such that g is defined, capital G is defined from integral small g to capital small h f of t dt, such that this g and h are differentiable on closed interval a comma b, then this g is differentiable and g dash x is equal to f of h of x into h dash x minus f of g of x into g dash x. So let me prove the statement. So proof. So let capital H of x be the antiderivative of f on closed interval a comma b. It is also given that f is continuous on closed interval a comma b. So this would imply my capital H of x is differentiable on closed interval a comma b, and my h dash x is equal to f of x, right, for all x. So let me number this as 1. Okay, so I know what is my g of x. So it's my g of x is given as integral small g of x to small h of x f of t dt. So we know that capital H is a antiderivative of small f. So that means h dash x is equal to f of x. So by second fundamental theorem of integral calculus, this will be f at h of x minus f at g of x, because second fundamental theorem says that it will be evaluated at endpoints. So I should say at antiderivative I need to calculate. So h is antiderivative, so h at h of x, and this will be h at g of x. Reason for this: by second fundamental theorem of integral calculus. Let me number this as 2. So because this will be evaluated on the antiderivative at endpoints. So h is an antiderivative. So capital H is an antiderivative of small f. We can write down this. Now see, this h is differentiable. So the left hand side is differentiable, right hand side is differentiable. Definitely RHS will be differentiable. So G is differentiable. So let me differentiate on both sides. So differentiate to with respect to x. So what I'll get is as follows: g dash x is equal to, so this derivative is h dash of capital H dash at small h of x into h dash x. So I'm using the chain rule minus capital H dash at g of x into g dash x. So this is chain rule of differentiation by chain rule. So, but my h dash is f. Expression 1 says that h dash is same as f. So instead of h dash, I will write f. So f at h of x, h dash x minus f at g of x into g dash x. So this is how the g dash x is evaluated. This theorem is highly useful for the problem uh, based on the there are problems where the capital G dash will be asked. So let's have some example. So if capital G of x is equal to integral cos x sin x 1 upon 1 minus t square dt, question is find G dash x. Well, you can see you can relate this question with the previous with the theorem. So here you can see that this is my small h, this is my small g, this is my small f. So let me write down f of t as 1 upon 1 minus t square. Okay, so 1 minus t square is a polynomial. So being a polynomial, it is continuous. So 1 minus t square is continuous. Then further, this function is defined at t is not equal to 1. So we are assuming the domain which we are covering is do not have the value of plus 1 and minus 1. So this should be clear, because f is not defined at plus 1 and f is not defined at minus 1. So in fact it is discontinuous at plus 1 and minus 1. But well, we will have a domain which will not cover plus 1 and minus 1. So this function 1 upon this reciprocal is continuous. So constant function, and the denominator is 1 minus t square. So ratio of this two function. So while taking the reciprocal function is continuous if this 1 minus t square is not equal to 0. So we assume here t is not equal to plus 1 minus 1. So we are excluding the domain which do not cover the plus 1 and minus 1. Further, my small h of x is cos x, small g of x is sin x. We can see that they are a differentiable function. Why they are differentiable? Being a trigonometric function, they are standard functions, so they are differentiable. So we can, this is continuous. We can have the domain which do not cover the plus 1 and minus 1. So that one should note, right? Okay, so then how will I find out this g dash x? So then my g dash x will be, it is 1 upon 1 minus cos square x into derivative of cos square x dy dx of cos x minus 1 upon 1 minus sine square x into dy dx of sine x. Okay. Which is same as 1 minus cos square x. So this is minus sine x minus 1 upon 1 minus sine square x. This is cos x. So this is fine. So you can even 1 minus cos square is sine square x and all. So this is sine square x, so minus 1 upon sine x minus 1 upon, this is cos square x, so cos x. So g dash x is cleared. So here I just said continuous. You can say on open interval minus 1 to 1. That's fine. Well, there are one more example I would like to take. Second example, g of x is equal to integral 3 to x is to 5 2 plus t dt. Find g dash. So you can see this is continuous 1 plus t, 2 plus t being a polynomial, it is continuous. 3 is a constant function, differentiable. X is to 5 is a polynomial, it is differentiable. So g dash x is straight away it is 2 plus this x is to 5. Instead of t we will then dy dx of x is to 5 is 5x is to 4 minus 2 plus t, instead of t we will write 3 into derivative of 3 is 0. So the answer is 5x is to 4 2 plus x is to 5. Well, this covers the Leibnitz rule. Now we will have a definition of Riemann sum and problem based on the Riemann sum. So, let f is function from closed interval a comma b to r be a bounded function let small p is equal to a, which is equal to x naught x1 xn is equal to b be a partition of closed interval a comma b choose any ti that we will call it as a tag from xi minus 1 comma xi for all I goes from 1 to dot 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 n. Then Riemann sum is denoted by SPF and defined as SPF is equal to summation I goes from 1 to n xi minus 1. Now here we will have f at ti. You can see this Riemann sum has a similar means like we had defined upper sum, lower sum. In upper sum, instead of f of ti, we had capital Mi, where capital Mi was a supremum in that interval. Now, in lower sum, we had small mi, where small mi was the infimum. Now, here capital Mi, small mi, instead of that, we have f of ti, where ti is a point between xi minus 1 to xi. So, it's very clear that my f of ti lie between small mi to capital Mi. So, and if you multiply that with xi minus 1 to xi, and then if you take the summation, then you will realize that uh, your Riemann sum lies between the lower sum and upper sum. So let me write down that a small remark. Clearly, f at ti always lies between small mi to capital Mi. Now I am not writing what is small mi, capital Mi. It is very clear. Small mi is a infimum and capital Mi is a supremum. For all I goes from 1 to n. And if I multiply this with xi minus 1, and then if I take the summation over it, then I will get LPF is always less than equal to SPF, which is less than equal to UPF. So this clearly states, this clearly shows that your Riemann sum lies between upper sum and lower sum. The next definition, that Riemann integrability using Riemann sum. So a function f from closed interval a comma b to r is said to be R integrable if limit as norm p goes to 0, SPF exists and is unique. Where P is any partition P is any partition of closed interval a comma b. Further, the unique limit, that is limit as norm p goes to 0, SPF is equal to integral a to b f of t dt. So if I want to check the Riemann, if I know the function is Riemann integrable, then the integration of this is basically just find out the, as norm p goes to 0, SPF. If I could find out this limit, then I will get the integral value of f. Right. So let's have a question based on it. Prove that f of x is equal to 3x plus 1 is R integrable on closed interval 1 comma 2. Okay. So what I'll do, I'll find out the limit of SPF as norm p goes to 0, And if that limit exists and if it is unique, then we will say that the function is R integrable, and that limiting value is basically the integral. So let me take the partition. So let P be any partition. So I will have a best partition as a Pn instead of P. I'll say Pn. So P1 plus 1 by n, 1 plus 2 by n, dot 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 1 plus n by n, which is equal to 2. Be a partition of be a partition of closed interval 1 comma 2. Okay, so let me find out what is SPF. So SPF is equal to summation I goes from 1 to n f at ti into xi minus 1. So summation I goes from 1 to n f at ti. So xi minus 1. So xi is 1 plus I by n minus 1 minus I minus 1 by n, which is same as summation I goes from 1 to n f at ti. So this is 1 and 1 will get cancelled. So I minus this will be I by n straight away if you subtract this. Now what is a Ti? What Ti should take? So it is very clear, we in our Riemann Sum we said where does Ti belongs? We choose any Ti between xi minus 1 to xi. Now here what Ti I should select, that is important. So I will take Ti here as a xi only, because where does Ti belongs? Where Ti belongs to xi minus 1 comma xi. So let us take Ti, let Ti is equal to xi, and what is xi? 1 plus I by n. So this is equivalent to saying that summation I goes from 1 to n f at 1 plus I by n I upon. It is not I upon n. I think it, yeah, how it will be. Here it will be, let me write down this, I minus I plus 1 upon n. Yeah, it will be 1 by n, correct. Yeah, this will be 1 by n. Okay, so this 1 by n is anyway constant. So summation I goes from 1 to n. What is f? F is given to be 3t plus 1, if I'm not wrong. F of x is 3x plus 1. So f of t is, yeah, 3 times 1 plus I by n plus 1. Correct? Yeah. So this is 1 by n. So this summation I goes from 1 to n. So 4 plus 3i upon n. So 1 by n. The 4 added n times, so it will be 4n plus. I hope this everybody knows how I'm doing this. So 4 times summation 1 I goes from 1 to n plus 3 by n in anyway goes outside, so I goes from 1 to n. So 1 by n. So let me write down 1 by n outside. So 4, 1 added n times, so it is n plus 3 by n. So this is 1 plus 2 plus 3 dot 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 up to n, so it is n into n plus 1 upon 2. So this n will get cancelled. If I multiply this 1 by n inside, so it will be 4 plus 3 by 2, 1 plus 1 by n. So it is 4 plus 3 by 2 plus 3 by 2n. So 8 plus 3, 11 by 2 plus 3 by 2n. So my SPF is basically 11 by 2 plus 3 by 2 n. So let me find out as limit norm p goes to 0, what is SPF value. Norm p goes to 0 means basically the maximum distance between any 2 points in a partition is 0. So you can see how my partition is defined. I have defined the partition in n terms. So the maximum distance is 0. So it is equivalent to saying that if I increase the points, if I n instead of n, if I take n goes to infinity, that means the distance between the 2 points is very, very small. That will approach us to 0. So it is equivalent to saying that limit as n goes to infinity SPF. I should say SPNF because instead of P I have PN everywhere. Yeah. S. So when I take Pn, so here n goes to infinity f. So this is same as limit as n goes to infinity 11 by 2 plus 3 by 2n, and this 11 by 2 integration limit is 11 by 2 plus 3 by 2n limit is 0 as n goes to infinity. So this 11 by 2 is a unique. So this is basically, this would imply f is R integrable. F is R integrable, and the integral value from 1 to 2, that f of x dx is equal to 11 by 2. So even in your 12th standard you must have this. If I 3x plus 1 इसका अगर integration निकालेंगे तो I am sure that you will get 11 by 2 only. So that you can verify. Okay, so here is a quick homework for you all. You can show that f of x is equal to mod x for all x between -1 to 1 is R integrable. And you can use the Riemann sum idea to find out the integration value. Right. So there is one more problem which normally we have asked in the practical also. So let me take that quickly. Evaluate limit as x goes to 0, 1 by x integral 0 to x e raised to x square dx. Right. So let me calculate this. So this is equivalent to saying that limit as x goes to 0, capital, instead of capital Fx, let me use capital G of x upon x. Where what is capital G of x? The capital G of x is integral 0 to x e raised to x square dx. Okay. So if I replace x is equal to 0, so it is very clear that this e raised to x square is an exponential function, is continuous. So if it is continuous, then this g of x is indefinite integral of this. So by first fundamental theorem of integral calculus, my g is differentiable, capital G is differentiable, g is differentiable, and g dash x is basically my f of x, but f of x is equal to e raised to x square only. So here I can apply the first fundamental theorem of integral calculus. Now how will I going to use this in this problem is as follows. Now, if I replace what is my g of 0, my g of 0, capital G of 0 is integration 0 to 0, which is anyway going to be 0. So numerator is 0. X, when x is equal to 0, denominator is also 0. So it is 0 by 0. So we can apply, it is an indeterminate form. So we can apply the L'Hospital. So it is L'Hopital rule. So it's L'Hospital or L'Hopital, they are one and the same. So what it says, you find out the numerator limit, derivative and denominator derivative. So g dash x upon x ka derivative is 1. Okay, so let's find out so now we know what is g dash x, and this limit is basically g dash at 0, and g dash is e raised to x square, so e raised to 0, so it is 1. So we have find out, we found the limit as x goes to 0, 1 by x integral 0 to x e raised to x square dx as e raised to 0, which is 1. Well, so this problem is basically one of the problem in the practical number 2, so which might help you to this kind of problems are not difficult. So one can find out, one can use the fundamental theorem of integral calculus to get the solution. So thank you for attending, watching the lecture.